Hello, my name is Andrew Porky. I'm currently a senior here at the University of Michigan, majoring in computer science, as well as pursuing a minor in complex systems. And today I'm here to share the work that I did on my honors capstone project, where specifically I took a look at modeling policies to mitigate an epidemic. And throughout this project, I was advised by Professor Luis Simon, a professor both in the Department of Complex Systems as well as the Department of Ecology and Evolutionary Biology. So first off, sort of what got me interested in this project? So as I'm sure many of you know, we're currently living through a global pandemic. So we've been living through the COVID-19 pandemic for about the past 2 years, and it's raised a lot of uncertainty about, how could we best navigate this pandemic? Were there some decisions we could have made early on in the virus's spread that would have put us in a much better position today? And really, I wanted to tackle this project to try and address, some of this uncertainty, try and see if there's anything we can do to learn about what the best policy might be to navigating a pandemic. And then additionally, a problem like this really is well suited for someone with a complex systems background. So a lot of the techniques that I've used in this project I learned through the coursework for my minor, so it really was a good pairing there. So throughout this project, there were sort of three main research questions that I was interested in tackling. First being, how can we best stop a pandemic? So specifically, what I wanted to do was find a set of mitigation strategies that together worked well to prevent the virus from spreading and prevent people from dying from the virus. So those are two of the big things that I wanted to find first off. The second big question that I wanted to answer is, are saving lives and protecting the economy mutually exclusive goals? So is it possible to both save lives and protect the economy in a pandemic scenario, or is it only possible to do one or the other? Then lastly, the last question I wanted to take a look at was, how does non-compliance affect how an epidemic virus spreads? So say you have all of these mitigation strategies in place. If you have people in the population that do not listen to them, how does that affect the spread overall? And are you still able to sort of stop the virus even if you have these people that are not complying with the strategies set in place? So one of the main tools that I used to tackle this project was an agent-based model. So for those of you that don't know, an agent-based model is a computational model where basically you focus at the agent level, so each agent is able to keep track of their own attributes. And then what you're able to do is define some very simple rules that's able to basically guide the behavior of the agents, and you're able to observe some very interesting complex behavior through that very simple rule set. So specifically for my agent-based model, I developed it in C++ using the Qt framework. Some of the specific attributes that the agents keep track of are their age, they keep track of their health status, they have a wealth associated with them, as well as a set of locations that they visit. Every agent has a home, work, school, and leisure location, and they're able to move between those locations throughout the day according to a predefined behavior chart. So there's a few different behavior charts, both for adult and child agents. And then there's an economy built into this model as well. So basically, agents are able to gain or lose wealth depending on which location they're at. And it's really, just the simple interactions between agents is able to build a complex economy, which is really one of the advantages of an agent-based model. So you're able to observe economic growth, economic downturn, all of these really, complex processes, even with just a simple model like this. And then additionally, I use the Sears epidemiological model. So that stands for susceptible, exposed, infected, recovered, and then susceptible again. So basically, agents, move through these stages linearly. So all agents start as susceptible, then one initial agent becomes exposed, and that's sort of how the virus starts in the community. And then that agent moves through and becomes infected, and then they become recovered, and then after a period of time, they go back to being susceptible, they lose their immunity. So both exposed and infected agents are able to spread the virus, with infected agents spreading it with a higher probability, as well as infected agents are able to die from the virus, where exposed agents are not. So those are some of the implementation decisions I made when creating this model. So the second big tool that I use to sort of tackle this question is the reinforced algorithm. So this is an example of a deep policy gradient algorithm. So basically what that means is it uses a neural network, and what that neural network learns is a policy for how to best solve a problem given the current state of the simulation. So specifically how this applies in this project is the neural network receives a state vector from the simulation. So the state vector contains a few different things. So it contains some information on the number of cases, number of deaths, as well as the proportion of agents in each of the compartments, so whether they're susceptible, exposed, etc., as well as it receives a little bit of economic information, so the unemployment rate as well as the the percentage change in economic value over a period of time. And then what this network is able to do is it outputs the probability that each mitigation strategy should be applied. So basically what it does is it says which mitigation strategies are best suited to solve the problem in the given case. So some of the mitigation strategies that I defined include, for example, quarantining, contact tracing, as well as there's some government assistance. So for example, unemployment and stimulus strategies. So really, what this network is able to do is learn based on, what current state the simulation is in, which of those strategies should we apply, to best stop the pandemic. And the really interesting thing with this algorithm is you can change the reward function to focus on different criteria. So specifically, I took a look at a reward function that focused on the pandemic, it focused on the economy, and then it focused on both. So the pandemic reward function focused only on reducing the number of cases and deaths. The economic reward function focused on economic growth while keeping unemployment and homelessness low. And then the dual reward function combined the two to sort of look at both and optimize both of those different parameters. So here we have a video of the model in action. So as you can see, the agents, as they become exposed and infected, they go into darker and darker colors. So orange is exposed, red is infected. This strategy was specifically trained using the economic reward function, so it's rewarded solely for keeping the economy growing. And what you can see is the strategy actually learned sort of to do nothing. So as you can imagine, one of the good ways to keep the economy growing well is as the virus is spreading, just sort of do nothing. So allow the economy to continue functioning as it normally would. And this does lead to some very good economic results. However, this leads to some, needless to say, horrendous public health results. So specifically, this policy ends up with a mortality rate of about 10%, which is, incredibly high. So it's definitely not a strategy recommended in real life, but it is one that was learned strictly focusing on the economy. So next up, I have a video of a policy that was trained with the dual reward function. So it focuses both on the economy and the public health side of things. And this strategy sort of uses a trifecta of strategies. So specifically quarantining, contact tracing, and lockdown. And this type of strategy appeared regardless of what reward function I used. So even focusing solely on the economy, this strategy emerged, and it's interesting because it would seem to indicate that knocking the virus out quickly and allowing things to return to normal as fast as possible is actually an optimal outcome, even if all you care about is the economy. So this sort of strategy, using that trifecta of different strategies, is able to achieve both optimal public health outcomes with a low rate of death, as well as optimal economic outcomes by keeping the economy growing and keeping unemployment low. So here I've got a table that shows the results of all of the different strategies that were learned. For each different reward function, there were 2 or 3 strategies that came up. One thing you can see, as I have highlighted, is that sort of contact tracing strategy that uses contact tracing, quarantining, and lockdown appeared regardless of which reward function is used. So that really does seem to indicate that that is the optimal way to stop the virus, and while also keeping the economy working well. And additionally, it achieved probably the best results, whether you're looking at the public health or the economic side of things. One thing to notice down in the bottom 2 rows, those are 2 strategies trained with non-compliance, baked into the population. So it's interesting to note that that really good contact tracing strategy, once non-compliance is in place, it's unable to stop the spread of the virus. However, it is able to reduce the number of deaths, sort of by flattening the curve and reducing the number of concurrently infected agents. So what that would seem to indicate is when non-compliance is in place, really the best thing that you can hope for is just reducing the number of deaths. There's not much you can do to preserve the economy, and there's not much you can do to reduce the spread. So definitely non-compliance is a huge issue when it comes to stopping sort of an epidemic. And then another interesting thing to observe is there are a few different cases where a total lockdown strategy came about. So basically locking down everything for as long as it took for the virus to die out. And the issue with that is it produced very good pandemic results, but the economy was just in tatters. Specifically, the last row of the table has the total lockdown strategy evaluated in a non-compliant population, and you end up with an unemployment rate of about 60%. So clearly that's that's just a massive number. So really the benefits that you get from a total lockdown in terms of the economic side of things, it's not necessarily worth it when you look at the economic implications. And then lastly, talking about some of the key takeaways of this project. So specifically what I said before, contact tracing, quarantine, and local lockdowns, those three strategies together are sufficient to stop a virus. So you don't actually need a total lockdown to stop the virus and restrict movement. Those three on their own is enough. However, that does assume a compliant population. So once you start having non-compliance in the population, there's really nothing you can do to stop the spread. Really, all you can do then is to hope to reduce the number of deaths. The second key takeaway, it is in fact possible to save lives while also preserving the economy. Those are not mutually exclusive. In some cases, saving lives actually leads to the best economic outcome by knocking out the virus quickly. So that was a very interesting finding to see. One important asterisk to put there is that non-compliance makes this much more difficult. So the more people in the population that don't comply with the strategies, all in all, it makes preserving the economy much harder while focusing also on saving lives. And then, that sort of leads right into the last takeaway in that non-compliance, it just really leads to rampant virus spread. When non-compliance is in the population, there is not much you can do to stop the virus from spreading at all. And in honesty, it just worsens outcomes in every respect. So economic outcomes are worse, and then also the number of cases and deaths are much higher. So that's sort of a pretty high-level overview of the project that I went through. I do want to give a few special thanks, specifically to Professor Zaman for working on with this project. It was great to work with him. He was able to provide some great insights, as well as the Engineering Honors Program. It was a fantastic opportunity to be able to complete this research and work on a really topical research project, so I definitely appreciate it. And thank you for listening to my presentation today.